All right, in this segment, we're just going to go over basic Gaussian elimination. If you really don't remember anything about this, it's easy to find good resources on Khan Academy and a few other places. But let's just dive in here with Gaussian elimination. First thing is, it is a direct solution technique. We'll talk later in the lecture about some other ways to get answers, but this is, we have a matrix, we have a vector, we have another vector we need to find. We can directly solve for this and get the answer in a straightforward way without iterating or guessing, or that's what some of the other solution techniques would do. All right, so Gaussian elimination is a numerical method for solving a linear system of equations. All right, we know about our linear system of equations, n equations, n unknowns. We know that A is a square n by n matrix, and x and b are vectors that have n components in them. All right, so the basic approach is to use Gaussian elimination to reduce this system of equations to an upper triangular system, all right, which we can call u times x, same thing, equals y. So we just edit these guys by a series of row operations. And again, row operations, if you need to check on those, that's the adding and subtracting and multiplying of rows to zero these things out. If you don't remember that stuff, do check out the Khan Academy resources. All right, so we're going to convert from this original system to this system, and then we're going to solve this by backward substitution. All right, so let's look at this a little bit more. Just to remind you exactly what the process is, we start with the A matrix. On our first elimination step, we're breaking this down and giving us some names that we can use as we convert to algorithms. All right, our first elimination step, what we want to do is get rid of all the things below this first element. Okay, so we want to go down this column. Our next elimination step is going to be getting rid of, so this was the first column. Next elimination step, we get rid of the second column. And these guys, I'm just pointing out, are called pivots. All right, we know that if we, as we go down and eliminate these things, it's possible that when we get to one of these guys, it might be 0. All right, and then, so these are already called pivots. What you do is you row pivot. You trade rows around till you find one that has a nice a non-zero and non-small coefficient right here, because we're going to be working with these a lot. You remember, you have to divide these guys by the next guy to get rid of the to get rid of these coefficients, right? So you want to have like a nice number to divide things and subtract things. You don't want to start with, you can't start with 0, and you don't want to start with something that's really small, because that can lead to errors. All right, so that's the procedure. We need to just get rid of the stuff below the diagonal. These are called pivots along the diagonal, and we get rid of everything below them in subsequent steps. And as we edit these rows, we know that we're also editing our b vector as we go. All right, when we get done, we wind up with ux equals y, and we want to do back substitution. So this is the algorithm for back substitution. And you know, you start with the last one. You're like, this times x equals y. So that's really easy to solve for, right? Divide through by this, and you get x equals yn divided by this coefficient. All right, so that's the last row. And then you step your way back up the matrix, saying, well, I know what this x equals, so I can plug it in here and subtract this guy, put this over on the other side and subtract it from the y side, and then I can solve directly for that. All right, so that's what this is. This is, I want to know what x is. Well, it's this y on this side minus this thing substituted back in, divided by this coefficient. All right, and it matters what row you're on, how many of these you have to do. If you're just on the If you're on the first row, there are none. If you're on the second row, there's 1. If you're on the third row up, we're counting up now, there are 2. So that's what's going on here with this summation, is it says, well, what row are you on? Well, what column are you on in these guys, right? Because remember, these guys are, here's the diagonal, all right? And so we want to be to the right of the diagonal, so I plus 1. And it just says how many of these steps are between I plus 1 and n. If you're already at n, they're none of them. So that's why you just do this directly. All right. If you're at n minus 1, well, there's 1 there. So we need to subtract that off. Okay. And so the next segment will talk about how you actually do this in a computer. And I want to make a note right now that Gaussian elimination, the number of operations all right. If you look it up, you'll see it scales as n, I need a lowercase n, cubed, but it's not hard to get it to n squared. All right. So for purposes of our class, direct solution techniques scale as n squared. Okay. And what that means is if you double the number of nodes, your simulation time could quadruple, because your number of operations, that's how long it takes you to solve this thing, goes as n squared. So that is just a measure of if you have 1,000,000 nodes versus 500,000 nodes, that's not just a doubling, that's a quadrupling of the time it's going to take you to run your model. So that is just an early note about that kind of thing. All right, next, algorithms.